To share this session, I would like to invite Professor P.G. Siddeshwar from Christ University. To give a brief introduction about Tirupati Guri sir, he has completed his masters from Kakatiya University, Warangal, Louisiana State University for 3 years, before which he has visited Humboldt University, Berlin for 6 months. He joined Indian Institute of Science Mathematics Department in 2010. Currently, he is a professor in Indian Institute of Science, Bangalore. He graduated 8 PhD student and guided 5 postdoctoral fellow. He has published more than 55 journal articles in internationally reputed journals. We welcome you, sir, to deliver the keynote address in this 2 days international conference on advances in applied mathematics.
Okay, so let us get to the talk. Today I am going to talk on this, the title is Dirichlet boundary control problem. I am going to overview the kind of optimal control problems that people deal in the literature, and then I'll try to highlight what is the difficulty when you go for the Dirichlet boundary optimal control problem. Particularly formulating the problem itself, there are certain difficulties and there are many approaches that people proposed to resolve the issue, and we proposed one thing that actually is well suited for the numerical approximation, because at the end when we want to actually to relate the model to the physical system, you need to have a solution that you have to come from get some numerical method. So to develop efficient numerical methods, the model has to be appropriately designed. So there were difficulties in the earlier formulations. We try to resolve through our model. So it is as follows. I'll try to give the overview of optimal control problems, various kinds of problems, and then particularly focus on this, and then illustrate for the control problem governed by elliptic, and the other one is parabolic. So this is a recent work that I did with my student and my postdoc. So I assume that you know certain background, but if not, so D is the domain where the PD, the partial differential equation, which is actually the physical model, the D is the domain that is in, for simplicity assume it is in R2 with the boundary gamma. So L2D is that those who have done MSc would have seen that square integrable functions defined in D. In the measure theory course you would have seen, or in function analysis. H1D is that so this is the space, subspace of L2 . Can you, okay. Control L. You download the PDF and open through browser. If you open through the Adobe Reader, okay. So basically, you are going to deal with a PD, so you need the derivatives also. H1 is that the functions are square integrable, whose derivative is also derivative is in the sense of weak sense, which we will not discuss, but so it is, there is a derivative in some sense, which is also, the derivative is also square integrable, and H10 denotes what happened to this. not visible on the screen. So H10 is that it has a zero boundary condition because the PDs come with the boundary condition. So that's why you need this space. H of is, so you can think that a square integral function with this term of H of, the norm of is defined by the double integration which is finite. Okay, so the important thing is that the H of norm on the boundary is a double integration. When we use this double integration directly in some numerics, it doesn't give a sparse matrix, it leads to a dense matrix. So one should avoid using such double integrations. So for that, there is equivalent definition of this H of norm is that you take all the H1 functions, means the L2 functions whose derivative is L2, and minimizing this Dirichlet energy, the L2 norm of the derivative with the given boundary condition W equal to V. And so look at all W, such W's whose boundary value is V, and minimizing this gradient. So that is also equivalent way of defining H of. Indeed, the minimizer satisfies this Laplacian W is 0, it's a harmonic function. And the important thing is that this the map takes V in that takes V to the boundary value. When you restrict V to the boundary, it is the smoothness is reduced by half a derivative on the boundary. But this map taking V to its boundary value is continuous and it's onto function. So that means what is onto? So given any function here H of, there is an inverse which is H1 whose boundary values is this. So this is called trace theorem in PD literature. So I use these notations and this result. So what is an optimal control problem? So there are variety ways of various models. For the first one is distributed one. So what it is asking for is that you have to look for U. U is the state. You think that we are sitting in the room. U is the temperature that we want to control. You bring the temperature U close to UD. UD is the desired temperature. For example, you switch on AC, you put it digital disk, you want to put it at 22, 20, something like that, right? So that's a desired temperature UD, and U is the actual that you want to control. But how do you want to control? By giving the input Q. Q is the source that we give to the system. By giving suitable Q, you want to bring U close to UD. Inside the domain, domain is the gray area, and the boundary is del omega. So if you write in a simple mathematical framework, it is like there is a cost functional J, which is you have to bring this, minimize this distance between Y and UD. Basically, U is the one minimizer, so you have to bring U close to UD, and then the cost that you pay, that the Q is the source. Q is the source that you have to pay. That's a source that you have to give, right? So that you pay. So that is what it's added. It's an L2 function. So this is stationary heat equation, you can think. So minus Laplacian Y is P and Y equal to Z on the boundary. So boundary values are fixed, but you have to find P suitably so that this U and Q minimizes this functional. Basically, you bring the say U, the desired state, close to the given state UD. This is distributed because the source that Q or that the variable P is defined all over the domain. That's why it's distributed. The other one is Neumann boundary. So PD can have inputs, the source function and the boundary data. So through source function, when you give the input, it is distributed. But if you give the source through Neumann boundary data, it is a Neumann distributed, Neumann boundary control problem. The similar problem you can ask, so you want to control U close to UD inside the domain by giving proper flux, right? Flux Q through the boundary. So mathematically now the control is acting, the P is control variable, so PD is same, minus Laplacian Y is F, and but now you ask, the control is acting through a Neumann boundary condition, del Y by del N. The cost functional looks same, except that the cost that you pay is P is on the L2 on the boundary. So you have to minimize that functional subject to the PDE. So this is Neumann boundary control because the control is coming through the boundary data. The other one is Robin boundary control problem. So for a PD, you can associate Neumann boundary conditions, Robin and Dirichlet. So if you associate the control through Robin boundary condition, it becomes Robin boundary control problem. So here epsilon del y by del n plus y equal to p. P is the control, that is the input that you want to give to the system. So all these three models that I discussed just before, all these are all mathematically well defined, because the function space that you look, P is L2. So if you write down, if you multiply minus Laplacian y with a test function v and do some integration by parts, all that naturally fit into the formulation. You can use the functional analysis. For example, you can use the Riesz representation theorem in the Sobolev space setting and prove the well-posedness of all these three problems. The problem comes when you want to have a Dirichlet boundary control problem. So here, the same thing, that you want to control u close to ud, and we prescribe u, not the normal derivative or the source. So you want to prescribe u on the boundary as q, and to control this inside close to ud. So mathematically, it is now the Dirichlet condition, y equal to p. So when you prescribe the value of y on the boundary, it is Dirichlet condition. So that's why the name Dirichlet boundary control problem. So the problem, the same, you have to minimize this cost functional defined here, subject to the PDE, but the boundary condition y equal to p. Here both y and p are varying. So you have to choose proper p, which is when you minimize it becomes q, such that it minimizes this functional. Both the corresponding, for corresponding q, the state, the solution is denoted by u. So the problem is, what is the right space here? I didn't define what is the space. I just said there is some abstract space q. What would be the space q here to make this problem well posed? So that's where the problem starts actually. So for simplicity, I am discussing this distributed control problem, Dirichlet boundary control problem for a simple heat equation, steady state heat equation. You can also pose the same question when you have unsteady state equation, heat equation, or you have a Navier-Stokes equation, the fluid flow equation. Controlling, basically, you want to control the flow. In the case of Navier-Stokes, you want to control the flow by acting appropriately, controlling the velocity and the boundary, basically. So the model can vary, but the associate problem remains the same irrespective of what physics you take. If you take heat equation or the flow equation or something else, maybe some concentration to control. So Dirichlet condition is the one that creates a difficulty, but PD you can complicate it further and then look at the further difficulties arising with that. So the question is, what is the right space Q here? So naturally, when you want to minimize a cost functional, usually it is used the L2 spaces, because the square integrable, when you use a square integrable norm in the functional, it becomes differentiable, and you can use the all calculus on the function spaces, because this functional will be differentiable, and you can do that. So that's a natural choice, is to use L2 the boundary. But the problem is here, P is just L2 data on the boundary. It's a square integrable function. For example, a discontinuous function, step function, is a square integrable function, but it has to be the boundary data of a solution to a PDE. The solution to PDE should be a nice function, at least you expect that it is continuous, but the boundary data can be discontinuous because you are looking for an L2. So very weak regular smoothness on the P you are asking, and looking for a solution of a PDE whose boundary value is this. So you are actually, there is already a problem hidden, but how to study the well-posedness of this when P is very irregular, just L2 on the boundary, whether there is a solution to this PDE Y corresponding to P. So what you can do is that multiply this equation, the PDE, with some function psi, integrate, and F is Laplacian of Y. So you then integrate by part, use the Gauss divergence theorem or Green's theorem. So put one derivative and then you get the boundary data here, and then put one more derivative from y, so it will go to minus Laplacian psi, and then you have this is supposed to be plus sign, the second term. So y has to be p on the boundary, so you substitute that, you get p, and you have to now I have to check this equation for as many functions I want. So I can, in particular, I can pick minus Laplacian psi is some z, another PDE, and psi is 0 on the boundary. So that last term get cancelled, and then Laplacian psi becomes z. So I get nice inner product here, yz equal to f psi, and when I take that y equal to the p term other side, it will be like this. So the given data is on the right hand side, and then y unknown is on the other side. So if you work on the L2 omega functions, this inner product, the left hand side is integral over omega yz is the inner product on L2. So you can use Riesz representation theorem provided the left hand side, the right hand side is a linear functional on L2. Okay, so this way one can address the well-posedness of the PDE, but you are only looking for a PDE, so solution of a second order PDE which is only L2. So that means the solution is very weak, very irregular. But mathematically you can give the well-posedness of the problem through this setting. There is a very weak function satisfying this. So you can have now the first approach for dealing with the Dirichlet boundary control problem is that you minimize this cost functional, but subject to PDE, the PDE is written in a different form, where you can give the well-posedness of the PDE, and the control is coming from L2 on the boundary. So this is a well-posed problem, and it has a solution. And so this is a solution, so it has a minimizer, so and it's a differentiable cost functional, so the derivative you can equate to 0 and get the optimality conditions. Okay, so if there is the smooth function has a maximum or minimum at the interior point, the derivative is 0. So same thing here, you apply derivative on the functional, you get this system. So here u is the solution satisfying this in a very weak sense. So that's why y is u actually, the minimizer, and you have a first equation. And second equation is to it's optimality condition written in a different way using another PDE. It's called adjoint PDE. And then the adjoint PDE, which is similar to the original PDE, but right hand side is u minus ud. And the third condition is actually connects the adjoint state with the control. The control is q. Q is the input that you want to give, and you see that and this is the third equation is equal to the equation holds for all p in L2. So in other words, it's alpha q equal to del phi by del n, the normal derivative on the boundary. So it's a nice framework. It allows you to see this, but there is also another approach. So we want to allow this L2 on the boundary data, but when I have to deal with L2 on the boundary data, so the problem second order PDE, the solution will become very weak. So you do add some perturbation to this. That's what the Robin boundary condition. Add epsilon times of the normal derivative. So it's kind of penalization approach. So you can deal with that. So but the problem is when you go for, you can study theoretically at the PD level, you can study all that, but when you do for numerics, that epsilon parameter, unless epsilon is too small, it is not correspond to the Dirichlet condition. You have to make epsilon very small, and when you do computations, there is also mesh parameter, and you have to tune up both this in a certain way, which you need a lot of theoretical estimates, and sometimes you may overestimate, and then the numerics may become inefficient. So, but people studied this also. And the other is that, as I mentioned in the very first thing, that for a solution of second order PDE, when you look, the first derivative should be square integrable. That is what H1, and whose boundary values will be in this H of this another space. The right space that you look for the control is H of on the boundary. But HF has a the double norm defined on that boundary, which is not good for use in computations. What they did is that given any such function, there is a function whose derivative is in H1 and it is harmonic inside. So you can have for given such P H of, you have an harmonic extension which is H1 inside this. And then that H of norm is equivalently same as the gradient of UP in the inside. So you can relate this double norm with the norm that is interior. So you can replace this by that norm. I can define the cost functional. I don't want to use the double norm that is defined on the H of space, but you can replace with that map, which is a Steklov-Poincare map, which is given value P on the boundary. You will do the harmonic lift to the interior and take the normal derivative of that, del UP by del N. So this is what a Steklov-Poincare operator. So that H of norm is SPP. So I can work with this, avoiding double norm. So, but what happens is when you want to do numerics for this kind of fun, again, so when you do numerical discretization, you discretize this control, that H of space, and you discretize the H1 space, and you have the certain basis. So each basis function in the control variable, you have to do a harmonic extension. So when you solve numerically, if you want to create numerical solution, you need to have a very high dimension, and then that many times you have to do the Poisson solve. That means you have to solve the PD that many times, which is again inefficient. Okay, so the goal is that we need to do something differently so that numerics becomes efficient. First, just because the original very first one, it's good for computations, but it has a very irregular state. Computationally, you can see that if you use the L2 space and for the control, the state looks like this. This is the desired state. For example, something that temperature you want to profile, you want to keep like this in a given room. If you apply the L2 control, the temperature, the control, that one, the state U looks like this. It's supposed to be close to that. So you see that there are artificial layers introduced by this model at the corners. Whereas the approach that we proposed will do like this, which is closely matching to that. So that's a comparison. So the reason for this layers on the boundary is that if you look at the optimality condition, it's here. Q equal to 1 by alpha del phi by del n. Phi is the solution of a PDE with boundary value 0. So the normal derivative, the control is nothing but the normal derivative of the function whose boundary values are 0. If the domain has corners and then the function is 0 on the boundary and domain has corners, the tangential derivatives two directions 0. So it forces somehow the normal derivative at the corner to be 0 if phi is smooth. So that's why you see, because two independent directions, if the function is 0, the tangential derivative is 0, somehow the derivative will be 0 at that point if the function is smooth. Okay, so the calculus fact. So that's the reason it forces. So the defect is in the model actually. So it forces artificially, which may not be desirable, that these layers. That should be avoided. So what we proposed is that instead of looking the control from and a space that is defined on a boundary, you define all over, look for a control which is defined on omega, but you use that in the system only on the boundary. So we want P, but a smooth function defined on omega, and so you minimize that cost subject to this PDE. And also this optimal control community, what they want is that so if you pay a lot, you can get the work done, but you want to minimize the cost also, right? We don't want to overshoot the cost. That's why you put the bounds on the, so you don't want to have the value P is going infinity or minus infinity, so you put pointwise bounds on the, so that is actually admissible space and then subject to the same. But also here this model allows that you don't want to apply the control everywhere, apply only the part of the boundary. For example, you place AC only one corner, not entire boundary, right? So this model allows that. And then, so there is a nice framework when you do that. If you want to have a framework for this in a function space to use function analysis techniques, so and P is again defined all over omega, I can write y, the actual solution, this y, as a w plus p, and w plus p, when I substitute here and multiply with v and integrate by parts, I have this. So I can put p the other side, because both w and p will be unknowns, and then I can now look for the solution. For example, so for given p, there is always a unique solution w here. So given p, the solution f, that is denoted by y is w plus p. This is solution operator. So will not I'll not get into these details, but so when you write this, so we can, in the weak formulation, in the functional framework, you can define this, minimize this function subject to this PDE, this map. So that is basically minimizing that. That is, there is a unique control problem. So there are some, again, proof goes by some weak convergence ideas in function analysis. So we skip that. So it tells that there is a unique solution of the problem. And then important thing is that once you have the minimizer, what minimizer satisfies, right? From there we can try to solve the equation. So basically this is what we were minimizing. So S of f p is the y you are minimizing. So y is the function of f and p. So you write that. And this is the reduced functional, because everything is in one variable p. And you find the derivative at q, which is minimizer, and then that looks like this. And by introducing this adjoint state by this PDE, you get this inequality, because there are constraints on the control. It is not an equation, it will be an inequality. So we get this optimality system to be solved is the state u is w plus q, w is satisfying this equation. This is rewriting a Dirichlet boundary value problem in this functional frame, and there is adjoint state, and then the last one is relating the adjoint state and the control. But so this is a inequality. Once you have pointwise constraints, it becomes an inequality. And the last equation, so v is the function space, which is this is v here. It is the functions has vanishing on the boundary, which is 0 on the boundary, but it is not the case for the last equation. But if I restrict p, which is 0 on the boundary, then from the second it becomes, the right hand side becomes 0. So we get basically the control q which we want, which is the input, satisfies this Laplacian q is 0 and q is 0, and then like this. So it is very close to the other people approach. What they did is that they first lifted with the harmonic map and then did the optimization. But here we did the optimization, then it turned out to be the harmonic. So what it tells is that the cost functional is different, but at the end the cost that realized are same, because it's a harmonic function. So that's observation to be made. And then because of the inequality, so there are certain conditions. If there is qa is minus infinity, qb is plus infinity, so this the first equation satisfies. So here del q by del n is del phi by del n. So the normal derivative of the control is normal derivative of adjoint state, which is not the same for the L2 functional. L2 case, the q is del phi by del n. That's why you have the layers at the boundary. So because of this condition, you don't see that. So that's what you avoid the unnecessary layers and the corners. So we can, I'll quickly tell about how to approximate this. So basically do the finite element method. So a domain you triangulate with the triangles, and then each triangle is T and its diameter HT, and mu H is set of all vertices in a triangulation, and these are VHD is the vertices sitting on the Dirichlet part of the boundary. And the function space that you are using, VH, is piecewise linear polynomials which are globally continuous, and 0 on the part which is gamma d. Gamma c is the control part, gamma d is the Dirichlet part, and QH is the space that we use for solving the control. It's piecewise linear, globally continuous, and because we want to apply the bounds, you have to apply the bounds at the vertices. You can't do apply it every point. Then it becomes an infinite many unique constraint optimization problem. When you do the optimization, nonlinear programming, you want to have a finite in the system. That's why you can put only finite number of constraints only at the vertices. And just mimic the continuous problem and write down this over this finite dimensional spaces. Look the same, but then here it doesn't lead to a system like Ax equal to b, but it leads to a quadratic programming. So you need to use the nonlinear programming and then some the solvers. There are methods like primal dual active set methods. One can apply and then solve this, and you can prove the estimates that there are two situations when the solution is like a second order PD. You want two derivatives to be L2 integral. So you can go up to H2, but so if an epsilon is off, you can go up to H2 in the second. If it is epsilon close to 0, you can only just be H1. So depending on the domain. The boundary, if the domain is not nice, you may not get two derivatives, but somewhere between 1 and 2. So with that, regularity in both cases, first case is like this 3 by 2 minus epsilon, other case is 3 by 2 plus epsilon. On both cases, the method converges optimally, and then also can efficiently implement the method. And for some numerical computations, we took this example on some unit square, and the control is acting only on the unit square, only on the bottom portion, and the remaining kept fixed. So basically you give only inflow from the bottom portion of the domain, and there are some parameters you fix, and these are the solutions, exact solutions for the system, so that you can compute actual errors and then see. So they all converges at optimal rate. The solution is nice. So the conclusions for this one is that if you use that L2 on the boundary space to define the digital counter problem, it introduces layers which are not physically relevant. So that's not a good idea. And there is another approach by using energy space, because H of space corresponds to the trace map space of H1. There is a Steklov-Poincare map involved. With that approach, it becomes numerically quite expensive. You can't do that. So what we proposed is that computationally efficient and also gives a sufficiently smooth control. It avoids the layers, the artificial layers on the corners. And also that some optimal control problems look for not just y minus yd, you want to control close to this, but the gradient. So the state has to be H1, the first derivative to be in L2 to start even with that. So this first one, it cannot be applied to this. The second one can be applied, but that is expensive, we know numerically. So our approach can be extended to this cost functional as well. So we can do the same thing for parabolic PDs, which is the time, you involve the time. We took, so far what we looked at the stationary one, but you can also look for the same optimal control problem, but now governed by a heat equation with the time. So we can do that. I think, how much time I have? Shall I stop? 10 more minutes I can, okay, fine. So here that, so it's a heat equation, right? So del T u minus Laplacian u is F, and the Q is the control that we want to find the Q as well as u, minimizing this functional. So here now it is L2 square integrable in time and square integrable in space, and this is the first derivative is square integral both in space and time. So you look for such a nice control through this model, governed by this equation. So again the control space is defined by this. So the boundary of omega is split into two parts, what is the bottom portion and the top portion, and then the side portion, because the parabolic boundary is a cylinder, right? The boundary of the domain, the spatial domain multiplied with the time, the initial one, and then top one we don't consider boundary, but here it is considered in the portion of gamma d. You fix control because the control is important only on the lateral surface part. So, and then the control part is this, this lateral surface of the cylinder, and these are given f could be 0. Okay. So, this is the time dependent problem. Okay. So, you need to give function space again through, okay, this is a L2 inner product both in space and time, and this is the space that we are going to use for the both the state and the control, but it is L2 in space in the time and then square integrable in time, but it is the derivative is square integrable in space. So, like this satisfies. So, what the idea is that multiply with this nice function first, this equation, and then do the integration by parts. That gives a formulation, functional formulation like this. Okay. So, we get, once we have the well-posedness of the PD, then the map that going from control to the state U is well defined. Once you have that map well defined, we can talk about the existence of minimizer for this functional. Again, the standard theory, you can, for example, look at the book of Troeltsch on optimal control problems. There is a standard, there is a the standard theorem proved for in a general setting how you prove the existence of solutions to optimal control problems. The first thing is to have a well-posedness under this function norms. So, this problem should be well-posed, and then you can talk about the minimizer. Once you have the minimizer, you can find the optimality conditions for the numerical point of view. So, this is optimality conditions, like this is what the control q bar to be found, which is satisfying this inequality, because there is a, you have a pointwise bounds on q bar. So, otherwise it becomes, if there are no constraints, it becomes equation, and this is adjoint state. So, if it is a, this is a forward, the state equation is a forward heat equation. You start with the t equal to 0 and move forward, and the adjoint equation is a backward heat equation, and then the control equation is the elliptic equation in a 3D domain, space and time. So, it is a complicated system, but this can be handled in, numerically. You have one is forward heat equation, another is backward heat equation, and then there is a 3D elliptic equation in space, and 3D in the sense 2 space dimension, 1 space time. So, this is what elliptic operator. This is the Laplacian is the space del square by del x square plus del square by del y square, but then you add this time second derivative. So, this is again it is satisfies a Signoroni kind of problem in 3 variables. This is Signoroni problem, is a known problem, well known problem in contact mechanics. Basically, when you have bounds, so it does not allow to move arbitrarily beyond q and qb, then you have these inequalities. That is what the contact problems talk about. So, we do the discretization, divide the time interval into certain, the old interval 0t to small intervals, that is the usual time step. Time discretization we take, and then we take the space discretization again with the finite element spaces that defined like this. So, it is on each interval. So, you divide L2 I H10, this means, and then on each interval here, it is a polynomial of degree 0 in time, but in space it is H10. Okay. So, this is a, we have to use some discontinuous Galerkin framework, but okay. So, basically what you do is that here the equation, the PD here you multiply with a piecewise constant, the Sobolev function valued, Sobolev valued function, multiply here and do integration by parts on each time interval and assemble the terms appropriately, to get this. So basically you do this integration on each of these intervals, time intervals, and then integrate also on omega, you get this. Okay, so because you allowed discontinuities, because a piecewise constant approximation in time, so there are discontinuities at the time steps t0, t1 and so on. So you need to take into account, that's why you penalize these jumps at each time step. That should be minimized. So you put it in the formulation and then you write down, and this is the space for the state and adjoint state, and this is for the control. This is for the control, that you need to discretize the 3D domain. So if you discretize the space by triangles and you are moving in time is a straight. So if you have a triangle moving in straight, it's like a prism. So you need to use prism elements in a 3D for the control variable. So they are defined like this. Okay, and then use them, all of them, in this formulation. Looks bit complicated again, but you can use the nonlinear programming techniques, which is primal dual active set method, to solve this. You need to kind of semi-smooth Newton method you have to apply and then solve this. So again, there are error estimates which are optimal, and we test this with this numerical example. So when we just want to advise the people who work in numerics, how do you come up with a model with a known solution so that you can compute the errors exactly, so that you can see your method performs. What you do is that you start with the known solution, you pick up some function which satisfies the boundary condition and put it that in the PDE and get the data. Okay, we do reverse. You take the data and finding solution is hard. That's what actually we want. But for numerical computations, you pick up a function which satisfies the boundary condition, put it in the PD, get the data. For that data, we know the problem has unique solution, so this would be the solution. So you can test all the computations with that. So that's why F is this, UD is the data is this, and then parameters, and then we could see that the optimal rate of convergence both in space and time, with respect to space variable and with respect to the time k. This one time is sigma is this one is okay. So these are the references. Thank you. So the first paper, this was the first paper introduced the L2 on the boundary control. So this was the one in 2006. So they proved some estimates and at the PD level and then at numerical level, and these estimates were refined by these people recently. It's not this one. Should be other paper. Okay, it's missing. So they did it some 2014 or something. These people did improve the analysis, and this was the first we came up with our approach, then applied it to the time dependent problems, and then with constraints. And this is the paper which they used Teklo-Payyankar map. So, and this is the one that it resolved an issue of proving optimal error estimates for contact problems, because our problem is related to the contact problem. So in the setting of contact problem, Signorini problem, they proved optimal order estimates. It took some 20 years to prove. This was the kind of work that settled the issue after so many years. So we used that result ideas in our papers. So thank you.
If there is no questions from students, I would like to ask one question. Sir, that Poincare map, what you have used here,
yes.
What is the role of that in this control system?
Here, right?
Here.
So it's actually in this case, it's the way it is defined is a positive semi-definite operator. It is actually what they wanted. See here, you want to use this space H of, which is defined on the boundary using the double integration, which is complicated. You want to avoid that. So what they did is that first do the harmonic lift of that, which is well defined. Once you do the harmonic lift and then take the normal derivative, what happens is that the h of norm of this is, you can prove that it is the gradient of UP, the harmonic extension. Okay, h of norm of P on the boundary is the gradient of the harmonic extension. The gradient of UP, if you look at, if I do this square it and square it, I can write grade UP inner product. And then do the integration by parts. If I use that its harmonic function, I get this term del UP by the harmonic extension times P. Okay, so if the definition is that the Steklov-Poincare map, the definition is that you take P on HF and then map it to the normal derivative of its harmonic extension. That's the Steklov-Poincare map. So that's what it happened to be Steklov. They want this connect, through this connection, you see that the rightmost and the leftmost in between, that is what it's setting. So if you denote by SP, that's the Steklov-Poincare map, which becomes positive semi-definite. Okay.
Actually, Poincare map, what we use is to see the one section of the, suppose we have a chaotic system or this one, to give the upper view of the chaotic system. That means we cut the plane in a particular map. So can we relate to that also?
Is the same map? I don't know if it is the same map. It
That
may
is
be
actually
different
we
map.
use
The dynamic,
Poincare map.
yeah, but Poincare map for that setting could be a different map.
Okay. Thank you, sir.
Is a Poincare Bendixson related? And these two are different things. Yeah. Yeah, that's from the company. Yes, sir.
Actually, I have studied optimal control theory as one of my papers in MSc. So we were taught about this Pontryagin maximum principle
Pontryagin maximum
for
principle,
the
yeah.
existence.
Yes, yes, yes.
For these type of problems, what type of maximum principles are used?
So basically, that is for Pontryagin maximum principle is basically for the OD system. Yeah, so there is some kind of rank conditions to satisfy for that. But here we don't encounter such thing in this kind of thing. Yeah, it comes as long as the functional is convex and the solution map is well defined. So that, yeah, visible, right. So there, because of the number of variables and equation, you need to have a match. So that principle comes there. Yes. Huh?
I have one small question.
Sure, sure.
When you are considering the functional subject to the PD,
PD.
and at one point I think you did mention that with the Dirichlet condition, you introduce a perturbation
Yes, yes.
to involve the normal derivative. So if epsilon is very small,
Correct.
then that would be the Dirichlet. And
This is close to the Dirichlet.
close
Close to the.
to Dirichlet. So does it mean that if we consider epsilon very large, you have the Neumann problem, and
Yeah, it both limits you can
yes,
talk about.
and
Yeah.
if you have epsilon finite, you would have the Robin
Robin condition.
Robin sort of condition.
Right.
Okay. And one more thing is, I think you discussed about elliptic and parabolic. In general, I understand that hyperbolic problems are hard.
Yeah.
So does it mean that is the reason why you did not consider the hyperbolic problem?
It's not that, but say, I work, so far in my career I looked at parabolic and elliptic, but hyperbolic people do study. For example, Professor Veerappa Gowda, they studied optimal control for the hyperbolic PD as well. So we can do that. Only thing is that the setting will be different. At least there is a natural extension from elliptic to parabolic. We can work with the wave equation for it. Wave kind of hyperbolic PD. The second order wave equation we can apply. But to the first order hyperbolic things, it is a different setting one has to do.
Telegraph type of equations, or
Telegraph,
which has both features.
it changes the nature,
Yeah.
right? Yeah. So if we address once if we understand how it is for the say second order wave equation, then maybe combining these two we may address the telegraphy equation. I feel, I mean, that's good.
Thank you very much. Any other question? If there are no questions, then we shall thank Professor Tirupati Gudi for the wonderful talk. Thank you very much.
So I request Professor P.G. Siddeshwar sir to come over the dais and hand over a memento as a token of gratitude. So I thank Professor P.G. Siddeshwar sir for sharing this session. So we have next session, the invited talk by Professor P.G. Siddeshwar, sir from Christ University, and Professor S.K. Narasimhamurthy, sir from Kuvempu University. So even though there is a tea break due to short of time, so we are going to serve the tea inside this hall only. So we are going to start the session now. So I request Professor R. Rangarajan from University of Mysore to share this session.
It's my great pleasure to introduce Dr. Pradeep G. Siddeshwar sir.
So welcome to all of you to this invited talk, first invited talk session. So I'm very glad to introduce Professor Pradeep G. Siddeshwar sir. He is highly qualified. He has got FI MA from UK and also FNAC, a very prestigious distinction, academic distinction. And he is senior most professor, served Bangalore University. Also now presently is Director of Research and Development Cell, Director Center for Mathematical Needs, Christ University, Deemed University, Hosur Road, Bangalore. And he has a very high citation.
WhatsApp.
Overall it is
WhatsApp
4066 and H index is 35 and I-10 is 103. So let us give a big applaud. So it's very needless to say that about his MSc and PhD, but he got MSc from Karnataka University, PhD from Bangalore University. He hails from Uttara Kannada, Gokarna, if I am right, sir. Yeah, it's not mentioned here. It's my own. And he has guided 23 PhD students, also postdoctoral students. And he has visited many countries, and his collaboration is more than 30 researchers, India and abroad. He got many awards and recognitions. President of India Award in 1983, Young Scientist Award in 1992, Indian Mathematical Society Prize in 1993, Japanese Society for Promotion for Science Fellowship, William Monk Fellowship of University of Hong Kong, Chanda Award from University of Windsor, Canada, Sir C.V. Raman Award, Royal Society Fellowship, London 2007, Fellow Institute of Mathematics and Applications, February 2008, Visiting Researcher, Shanghai University, Shanghai, and Visiting Researcher, University of Nottingham 2010,
Email ಕಳಿಸ್ಲಾ
Visiting Researcher and Researcher in Malaysia, Visiting Researcher in Chile, Fellow of National Academy of Sciences 2012, and many more are there. So I apologize him for not reading all of them, because we are very eager to listen to his lecture. And I am very proud to introduce such a distinguished academician and very senior most professor. I request him to deliver his invited talk. Thank you.